Hello learners, welcome to nios studio. Today we are going to talk about electric charge. We will explain the basic properties of electric charge and will also explain the concept of quantization and conservation of charge. Now let us come to the definition of electric charge. Electric charge is nothing but the amount of energy or electrons that pass from one body to another by different modes. Now, these modes can be conduction, induction, or any other specific method. Now, electric charge is of two types: positive charge and negative charge. Charge is present in every type of body. All these bodies have no charge because they are neutrally charged ones. Neutrally charged means they have equal amount of positive and negative charge in the neutral state. Symbolically, if we see, positive charge can be represented by a plus sign and negative charge is represented with a negative sign. Now, let us see the structure of atom where the electrons, protons are present in an atom. This is the structure of atom. We see that in the nucleus we have two types of particles. One is proton, that is positively charged, and other is neutron, that is having no charge. And electrons are revolving around the nucleus in shells. So, these electrons are negatively charged particles, and in an atom the amount of positive charge and negative charge is equal. Positively charged atom, when the number of positive charge is greater than the number of negative charge, such as we can take the case of sodium here. Sodium, that is known as a cation, Na plus, and negatively charged atom, the number of negative charge is greater than number of positive charge. Here we can cite the example of chloride ion. So, chloride ion is represented with a Cl minus sign. Let us demonstrate the positive charge body and negative charge body through figures. Now, this body has 5 units of positive charge and 2 units of negative charge. Positive charge plus 5 and negative charge minus 2. So, net charge is, if we add them up, the net charge is plus 3 units. Similarly, this is the example of a positively charged body. Now, we will draw the figure for a negatively charged body. Now, this body has 1, 2, 3, 4, 5, 6, 7. 7 units of negative charge, minus 7 units, and the positive charge is plus 2 units. So, net charge is minus 5 units. This is the example of a negatively charged body, and this is the example of a positively charged body. A positively charged body has excess of positive charge, and a negatively charged body has excess of negative charge. For an atom, only protons and electrons are responsible for the charge, as the neutron has no charge. The protons are positively charged particles in an atom, electrons are negatively charged particles. Now, symbolically, we can represent the charge by the symbol small q. The standard unit of charge is coulomb. Let us come to the basic properties of electric charge. What are the basic properties of electric charge? We will discuss them one by one. Number 1, the like charges repel each other. Then unlike charges attract each other. Third is charge is conserved. And fourth is charge is quantized. We shall take up them one by one. Now, in this figure you see one charge is positive, another charge is negative. So, they will attract each other. And in the second portion, you see we are having two positive charges and two negative charges. Two positive charges, there will be repulsion among them. Similarly, in between the two negative charges, they will also repel each other because they are like charges. Let us do this activity so you can see yourself. I am rubbing the comb with my hair and I have bits of paper in front of me. You can see the paper bits are being attracted by the charge comb. So, this is charging by induction. Now, we will explain the attraction and repulsion between like charges and unlike charges. This is a positively charged glass rod. This has been rubbed with silk and then it becomes positively charged. It is suspended by means of a sport. Then we are bringing another positively charged glass rod near to this suspended glass rod, which is also positively charged. We see through this arrow that this suspended charge rod will move away from this glass rod, which we are bringing near. So, when this is brought near, this suspended charge rod will move away this glass rod because both are having same charges. So, it proves that the like charges repel each other. Now, we will understand by means of a figure that unlike charges attract each other. Now, come to this figure. We are having a positively charged glass rod here, which has been rubbed with silk and it becomes positively charged. Then we are bringing another rod. This rod is made of ebonite and it has been rubbed with wool. So, it will become negatively charged. Now, when this rod, ebonite rod, is brought near this glass rod which is suspended, the glass rod moves towards the ebonite rod because both of these rods are having opposite charges. So, this schematically represents that unlike charges are going to attract each other. Conservation of charge. Charge conservation is that the total electric charge in an isolated system never changes. The net quantity of electric charge, that is the amount of positive charge minus the amount of negative charge, is always constant quantity. This is illustrated in this figure. Here you, in the yellow color, you can see that this is the duster and polythene strip is shown in a white color. So, before rubbing, both were uncharged. The charge, the positive charge and the negative charge were equal on both the polythene strip and the duster. But when you rub the duster with the polythene strip, you can well see in figure that the positive charge is more and the negative charge is less. So, we can say the duster is positively charged here and you can now see to the polythene strip. Polythene strip has more negative charge, the plus signs are very less and the negative signs you see are more in the polythene strip. So, effectively we can say that the polythene strip is negatively charged. Now, you take into account the total charge of the polythene strip and the duster. You add them up, the charge, net charge will be 0 as it was before the experiment, before the rubbing. This whole experiment can be summarized into 2 points, that the total charge of the system duster plus polythene strip is conserved. The second point is it is neither created nor destroyed. It is only transferred from one body of the system to the other. When the duster is rubbed, the less tightly bound electrons from the duster are transferred to the polythene strip. The duster, now which is deficient in electrons, will become positively charged and the polythene strip, which now has excess electrons, will become negatively charged. Now, we will discuss the quantization of charge. The total charge on a body is always an integral multiple of small e, where small e is the charge on an electron. The charge on a body can never be like 2.5 e or 1.5 e or 1.3 e. It has to be an integral multiple of small e. So, mathematically we can say that if charge is q on the body and n is the number of electrons and E is the charge on one electron, so this can be written in the form of an equation q is equal to Ne, where n can take values from 0, plus minus 1, plus minus 2, plus minus 3 and so on. E is the charge on electron and it has a value of 1.6 into 10 raised to power minus 19 coulomb. Today we have discussed the properties of electric charge in detail. Thank you. Hello learners, welcome to nios studio. Today we are going to discuss Coulomb's law and its representation in the vector form. We will explain the Coulomb's law of force between two electric charges and how it can be represented in terms of vectors. Now, we come to the definition of Coulomb's law. The Coulomb's law states that the force between two electric charges Q1 and Q2 is directly proportional to the product of two charges, that is, F is proportional to Q1, Q2. It is inversely proportional to the square of distance between the two charges. If it is r, then we can say that F is proportional to 1 upon r square. It is directed along the line joining the two charges. And lastly, the force between two charges will be repulsive if they are like charges, and it will be attractive if they are unlike charges. Now, we will explain it on the blackboard. Now, let us write the Coulomb's law in the mathematical form. F, the force between two charges, is equal to K Q1 Q2 upon R square. Here K is the constant of proportionality, Q1 and Q2 are the two charges and R is the separation between these two charges. Now, this constant K has been found to be equal to 1 upon 4 pi epsilon naught. Here epsilon naught is the permittivity of free space, as the spacing between these two charges Q1 and Q2 is free space or vacuum. If these two charges Q1 and Q2 are kept in a medium, then the force between these two charges can be written as F medium is equal to 1 upon 4 pi epsilon Q1 Q2 upon R square. So, you see, when we write the force between these two charges in a medium, epsilon naught is replaced by epsilon. Here epsilon is the permittivity of that medium, and the ratio of epsilon upon epsilon naught is known as epsilon r, the relative permittivity of the medium. It is the relative permittivity is also known as dielectric constant of the medium. We have seen that how we can write the Coulomb's law in the mathematical form. Mathematically, we can write that F in vacuum divided by F in medium, that is F upon F naught, is equal to ER, that is the relative permittivity. Now, we will explain the Coulomb's law in the vector form. Let there be 2 point charges Q1 and Q2. They are separated by a distance r. Let us come to the figure and see how the force forces these two charges. This is charge plus Q1, this is charge plus Q2. Now, the force on charge 1 due to the charge 2 will be in this direction, means it is from right to left, and then the force on charge Q2 will be in the direction from left to right. So, F12 and F21, they are in opposite directions. Now, if one of the charges is negative charge, means Q1 is positive charge and Q2 is a negative charge, then what happens to the forces between these two charges? Now, this is F12, this will be a force of attraction now, because this is positive charge and this is negative charge. So, it will be attracted towards it. So, F12 will be in the direction from left to right, and negative charge will be attracted by this positive charge. So, force on 2 due to this charge 1 will be from right to left. Again, you can see that F12 and F21 are oppositely directed. Now, we will understand these F1 and F2 in terms of equations. Let us write equations for F12 and F21 in the vector form. F12, force on 1. This subscript 1, 2 denotes that this is the force on charge 1 due to charge 2. Let us put vector sign on it. 1 upon 4 pi epsilon naught. They are separated within vacuum. Q1, Q2 upon R12 magnitude square R12 cap with a negative sign. Because you see, force on 1 due to 2, R12 is a unit vector. R12, you see there is a cap on this R12 which denotes that R12 is a unit vector, and it is directed from charge 1 to charge 2, means its direction is from left to right. You see the direction of F12 now. F12 is directed from right to left. So, the direction of F12 and the direction of R12 are opposite. So, we have introduced here a negative sign. Let us write equation for F21 now. F21 will be equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R12 magnitude square R12 cap. Now, you see the direction of F21. F21 is from left to right. It is from left to right, and R12 is also from left to right. So, they are having same direction. So, there is no negative sign. Now, if we compare these two equations F12 and F21, the right hand side of this equation is same except this negative sign. So, we can write F12 is equal to minus F21. Force on 1 due to 2 will be equal and opposite to the force on 2 due to 1. So, now we have clearly understood how the can be explained in the vector form, and we have also found that the force on charge 1 due to 2 is equal and opposite to the force on charge due to 1. Today, we have understood what the Coulomb's law is and how it can be represented in the vector form. Thank you. Hello learners, welcome to NIS Studio. Today, we will define electric field. We will find electric field due to a charge at rest and due to a system of discrete charges. Now, let us define electric field. The electric field at a point is defined as the electric force F experienced by a positive test charge Q naught placed at that point divided by the magnitude of the test charge. If we write it mathematically, then E will be equal to F divided by Q naught, where Q naught is the test charge. This equation is analogous to the definition of acceleration due to gravity. G is equal to F upon m naught, where m naught is the mass in the gravitational field F. Now, this test charge Q naught, which has been introduced to define electric field, it should be infinitesimally small, as given in this equation, E is equal to limit Q naught approaches 0, F upon Q naught. This can be understood from this figure A and B. First, we will discuss the figure A. Here, we are going to find the electric field due to the charge body, which is on the left, and the test charge is Q naught. So, this test charge Q naught is very, very small as compared to the charge Q. It is not going to disturb the charge distribution on the charge body. In second case, if the charge Q naught is nearly equal to the charge of the charge body whose field is to be determined, then it will definitely change the distribution of charge on the surface of the charge body, and it will result into a change in the electric force also. So, the adjoining figure A shows a uniformly charged metallic sphere with charge Q and a test charge Q naught, which is very, very less than Q. It means that the charge density per unit area is same around point A, B, C and D. The test charge Q naught must measure the force without disturbing the charge distribution on the sphere. In the figure B, we have the situation when Q is nearly equal to Q naught. In this case, the presence of the test charge modifies the surface charge density. As a result, the electric force experienced by the test charge Q naught will also change from F to F dash. Therefore, the test charge Q naught should be infinitesimally small. If it is not so, then the force measured will be different. Now, let us calculate the electric field due to a point charge. First of all, we will write the expression for the force between the test charge and the charge whose field is to be determined. Here the charge is Q and the test charge is Q naught. So, the expression for the force will be F is equal to K Q Q naught upon R square multiplied by R cap. Here R is the distance between the charge and the test charge Q and Q naught, and R cap is the unit vector directed from test charge to the test charge. Then, by definition of electric field, it is the force divided by the magnitude of test charge. So, E will be equal to F upon Q naught. So, expression for it will be E is equal to K Q upon R square into R cap. So, now we will represent the electric lines of force due to point charge. How the electric lines of force are depicted in case of a positive and negative charge are shown in the figure A and B. In a case of positive charge, the electric field lines are radially outwards, where in case of a negative charge, the electric fields are radially inwards. Now, let us define the unit of electric field. What is the unit of electric field? We will talk it out. In SI system, the force is in Newton and the charge is in Coulomb. So, therefore, the unit of electric field will be Newton per Coulomb, because the formula for electric field is E is equal to F upon charge. It is force per unit charge, so it is Newton per Coulomb. Now, we will talk about the direction of electric field, because electric field is a vector quantity. So, electric field is a vector quantity and it has the same direction as that of the electric force. Means the direction of electric field will be same as that of electric force. So, here the direction of electric field will be in the direction from Q to Q naught. Now, let us find the electric field due to a system of discrete charges. Here we are having different charges Q1, Q2, Q3. We are interested in finding out the electric field at point P. So, we will find it by the principle of superposition. Now, we will find the expression of electric field due to a system of discrete charges on the board. If there are number of charges Q1, Q2, Q3, they are at distance R1, R2 and R3 from point P. Let us write down the expression for electric field due to charge Q1. E1 will be equal to K Q1 upon R1 square R1 cap. E2 will be equal to K Q2 upon R2 square R2 cap. E3 will be equal to K Q3 upon R3 square R3 cap. Now, the total electric field E will be equal to vector sum of all these fields E1, E2, E3 and so on. E equal to E1 plus E2 plus E3 plus so on. We can write it using summation sigma K outside summation, then Qi upon Ri square Ri cap. Summation is from I equal to 1 to n. Here hello learners, welcome to nios studio. Today we are going to define electric dipole and electric dipole moment. We will also calculate the electric field due to a dipole in special cases. Let us first define electric dipole. The electric dipole is a system of two equal and opposite charges separated by a very small distance. The figure shows two charges minus q and plus q separated by a very small distance 2L. Now, let us calculate the electric dipole moment in this case. Electric dipole moment will be equal to either charge into the distance between them. So, it will be q into 2L. Now, SI unit of the dipole moment will be the unit of q into unit of 2L. Q is measured in coulomb and 2L is measured in meters. So, SI unit will be coulomb meter. Now, this electric dipole moment is represented with symbol P. So, let us write it down here. It is equal to P. Now, this P is a vector quantity. If it is a vector quantity, some direction should be associated with it. So, what will be the direction of P? Direction of P is always from negative charge to the positive charge. So, in this case, P will be directed from left to right. So, in the particular case, here the charge minus q is on the left and charge plus q is on the right. So, P is directed from left to right. Now, let us calculate the electric dipole moment in two special cases. First, we will take the case when the point is on the axial line of the dipole. Now, we will calculate the electric field due to the electric dipole when the point P lies on its axial line. Let us come to this figure. Here, this is the electric dipole. Charge minus q is here, charge plus q is here. They are separated by small distance 2L and the point P where the electric field is to be found. Let us find out the electric field due to the positive charge at point P. Let it be E1, then E1 will be equal to K Q upon R minus L whole square. It will be along AP. Why it is R minus L? Because the distance between point B and point P, it will be R. This distance is from the center. R is the distance from the center of the dipole to point P. So, the distance between point B and P will be R minus L. So, we have taken it here. Now the field at point P due to the negative charge, let us represent it with E2. It will be equal to K Q upon R plus L whole square, and its direction will be along PA. Why it is R plus L whole square? We are taking the negative charge. This distance is R. So, L has to be added to it. So, then it will become the distance between minus Q and P. So, we have taken R plus L here. So, E2 is equal to K Q upon R plus L whole square, and its direction will be from P to A. Now, from the scrutiny of these two relations E1 and E2, we see that E1 is more and E2 is less, because the denominator here is R minus L whole square. So, the net electric field at point P will be E, and E is equal to E1 minus E2. It will be K Q 1 upon R minus L whole square minus R plus L whole square. Then, doing the necessary mathematics, E will be equal to KQ R square minus L square whole square, and this is R plus L whole square minus R minus L whole square. It will be K Q R square plus L square plus 2LR minus R square minus L square plus 2LR divided by R square minus L square whole square. So, this comes out to be KQ 4LR upon R square minus L square raised to power 2. It can also be written as K 2 P R upon K2PR upon R square minus L square whole square. Now, this K is nothing but 1 upon 4 pi epsilon naught. So, electric field E will be equal to 1 upon 4 pi epsilon naught 2 PR upon R square minus L square whole square. Now, electric field E is a vector quantity. So, it will be directed along the direction of P, means it is having the same direction as that of the dipole moment, and dipole moment in this case is directed from left to right, negative charge to positive charge. So, electric field, net electric field is also from negative charge to positive charge, that is from A to B or A to P. So, now let us find the electric field in special case when L is very less as compared to R. L is very small as compared to R. In that situation, E will be equal to 1 upon 4 pi epsilon naught 2 p R taking dividing and multiplying by R square. So, it will be R raised to power 4 1 upon L square upon R square whole square. L square, when L is very small as compared to R, L square upon R square will be a very small quantity and can be neglected. So, the expression becomes 1 upon 4 pi epsilon naught 2 p upon R cube. This particular case has two basic significance. Number one, the electric field on the axial line is directed along the electric dipole moment, and secondly, the electric field due to this dipole will be proportional to the 1 upon R cube. Now, let us calculate the electric field in the second case when the point P lies on the equatorial line of the dipole. So, let us come to the board to find out the electric field due to a dipole on its equatorial line. Let us refer to figure A. Here we are having a dipole AB, charge minus q is here, charge plus q is here, and this is point P on its equatorial line, means on its perpendicular bisector. Now, the field due to charge minus q will be directed along PA. It is depicted by E2. Then the field due to charge plus q will be along BP. It is depicted by E1. Now, as E1 and E2, they will be equal in magnitude, but their directions are different. So, they are to be resolved into components. So, in the figure B, we have resolved E1 and E2 into components. This angle will be theta, this angle will also be theta. So, resolving E1 into components, it will be E1 sin theta and this will be E1 cos theta. Similarly, it will be E2 cos theta and it will be E2 sin theta, as magnitude of E1 is equal to magnitude of E2 is equal to E. So, E1 sin theta and E2 sin theta, they are equal and opposite. So, they will cancel each other. So, there will be no component of the electric field in the vertical direction. The net electric field will be along the horizontal direction only, and it will be E1 cos theta plus E2 cos theta. Now, let us write out the expression for E1 and E2. E1 will be equal to 1 upon 4 pi epsilon naught q upon R square plus L square raised to power half whole square, means 1 by 2 and 2 will cancel each other. So, the expression will be 1 upon 4 pi epsilon naught q upon R square plus L square. Similarly, expression for E2 is equal to 1 upon 4 pi epsilon naught q upon r square plus L square, because why we have taken r square plus L square? So this is L and this is R. We are supposed to calculate BP and AP. BP will be equal to r square plus L square under root. When we take the square of under root, it is simply r square plus L square in both the cases. Now, net electric field E will be equal to E1 cos theta plus E2 cos theta. It will be simply 2E cos theta, because E1 and E2 both are equal, which I have already written here in equation 4. Because magnitude of E1 and E2 are same, I have represented it by E. Substituting the value of E from here, 2 into 1 upon 4 pi epsilon naught Q r square plus L square. Now, let us write the value of cos theta also. Cos theta will be equal to base upon hypotenuse. So, in this case, base will be L. Hypotenuse is r square plus L square raised to power half. So, base is L upon hypotenuse is r square plus L square raised to power half, or under root, you may say. So, substituting this value of cos theta, we have this expression L upon r square plus L square raised to power half. Now, again writing the expression for the electric field. Using necessary mathematics, we have 1 upon 4 pi epsilon naught. This 2QL is replaced by P. We know that 2QL is nothing but P, the dipole moment. So, P upon r square plus L square raised to power 3 by 2. So, this is the expression for the electric field. We have found the magnitude of the electric field here. Now, what will be the direction of this electric field? We again come to this figure B. You see that the direction of resultant electric field will be direction from right to left, means it is directed in a direction opposite to the P, because P is directed from minus Q to plus Q, and electric field, net electric field will be directed from right to left. So, how we will write it here? E is equal to, with a minus sign. Why minus sign has been introduced here? Because E and P are directed along different directions. Now, let us take the special case when L is very, very less than R. We already know that the separation between the two charges is very, very less as compared to this distance R. So, what will happen to this equation? Now, let us find out the expression for electric field when L is very, very small as compared to R. Expression for electric field E will be 1 upon 4 pi epsilon naught P upon dividing and multiplying by R square. So, it will be R cube 1 plus L square upon R square raised to power 3 by 2. As L is very, very small as compared to R, so this term can be neglected. We are left with minus 1 upon 4 pi epsilon naught P upon R cube. Again we find out that the electric field E in this situation is proportional to 1 upon R cube. So now I will summarize the points which we have found here. The magnitude of electric field in end-on position is twice the field in the broad-on position, means the magnitude of electric field in case of axial line is double than the field on the equatorial line. This is field on the equatorial line, and the field on the axial line was 1 upon 4 pi epsilon naught 2p upon R cube. So when we compare these two relations, relation 1 and relation 2, comparing relation 1 and 2, we see that field on the equatorial line is half than the field on the axial line, and the field on the equatorial line is in opposite direction to the dipole moment, whereas in case of axial line, the direction of the electric field and the direction of the electric dipole moment were same. However, we find one similarity also. That similarity is, you see that electric field in both the cases is proportional to 1 upon R cube. So today in this lesson we have defined the electric dipole, we have defined the electric dipole moment, and we have found the expressions for the electric field in two special cases, when the point P is on the axial line of the dipole, and the second case when the point P is on the equatorial line of the dipole. Thank you.